The heading is a little long and awkward, I admit. It's literally the very last moment before we actually get to know how to differentiate and integrate trigonometric functions. But we've had a lot of groundwork to lay, and this is somewhat, I guess you could regard as the last piece. Okay. The heading is behavior of sine x and tan x for small x. It's not the same as the heading that's in the textbook, but I like mine better, which is why I put it there. Now, what I'm going to do right now is I'm going to show you a strange proof, but I want to give you first the intuition for why we would even embark on this proof to begin with. I remember this great teacher I had years and years ago, and he said, always guess. When you're uncertain about something, always guess and use your intuition, because one of two things will happen. You'll be wrong with your guess, in which case, no big deal, it was just a guess. Or you'll be right and you'll feel like a freaking genius, right? So what I want to point out to you, I want to remind the people who were in my class last year, and for those who weren't, this might be completely brand new to you. I want to talk about sine and tan and what they actually are in a very similar way to how I talked about what a radian was, and I somewhat redefined it for you. Okay, so this is our friend. Can you tell me what this is? You can tell me what this is, right? There's enough information, clues on here to tell you. This is the unit circle, right? I mean, you can see it's a circle. You got radius 1, and if it wasn't obvious enough, the equation is hiding over here, not doing a very good job at hiding. Okay. So you got the unit circle, and the reason why the unit circle should be a sensible place for your brain to go when you think about these objects is because trig, sine and cos and tan started with right angled triangles, right? It started with, you've got an angle, you've got a right angled triangle, you've got some sides, and then what did we define sine, cos and tan as in terms of a triangle like this? Yeah, very good. We said, hey, let's call this the opposite side from that angle. This is the adjacent side, and this one's always the hypotenuse. And then we just sort of compare different pairs. Opposite hypotenuse, opposite adjacent, you get the idea, okay? But then we realized at some point around late year 10, we realized that this definition's nice to start with, but it won't cut it. Because the only kinds of angles you will ever find in right angle triangles are acute angles, right? You can't get an obtuse angle in there if you've got a 90, a pi on 2, I should say. You'll only ever get acute angles, and there's lots more angles in the world than acute angles. So that's why we introduced this guy, right? Importantly, we redefined cos and sine as two things that are on the board right now. How did we redefine them? We forgot the triangles, somewhat. We said cos and sine were, can anyone tell me? Why am I saying it in that order? Cos and sine rather than sine and cos. Yeah, very good. See these coordinates here, right? These are the coordinates that correspond to the angle subtended at the center of the circle with the positive x-axis, right? And we said those coordinates are cos and sine, yeah? Which is why we got to much more useful things like, say, 90 degrees, right? You can't fit that in a right angle triangle either, but the cos of 90 degrees will be the x-coordinate, which would be, in this case, what's the x-coordinate up here? The x-coordinate up here is 0. So cos of 90 is 0. Sine of 90 would be the y-coordinate, which would be, now you can say it, 1, right? So, and then we can go over here, we can have negatives, all that kind of thing. Which was clearly, you can't have negatives when you're thinking about ratios of lengths, but we went much further, okay? So what I remind you of is that if sine is this vertical coordinate, then I can put sine on like this. Okay, so if I animate this, that blue line, however long that is, the length of that blue line is sine of that angle. Is that okay? You're okay with that idea? And you can see sine gets longer and shorter as the angle varies. And I'm just interested in acute angles for now because I'm trying to think about small values of x. Okay. Now, let me just hit pause on that. Now, I wonder, and we did it a long time ago, so I won't be surprised if you say no. But I'm going to put the people in my class on the spot and say, stop. How do I want to put the keyboard away. Go away. Oh, I feel bad for Mrs. Lees. Hope she's okay. There we go. Okay, so I'm going to put my class on the spot, and I'm going to say, who remembers we redefined sine and cos as y-coordinate, x-coordinate? How did we redefine tan? In terms of this, get away from this right angle triangle, get away from opposite and adjacent. Where on earth is tan on this? Because the answer to that question is why tan is called tan. Tan's an abbreviation, right? It's an abbreviation for tangent. And in this context, you're like, huh? What does tangent have to do with anything like this, right? Well, let me remind you, there's lots of ways to show you this, but this is, I think, my favorite and the clearest one. See that tangent there? That tangent? It goes from the point that's been subtended on the circumference down to the x-axis, right? Just like this angle is from that line to the x-axis, positive x-axis. That line is a tangent. I should say that interval. The length of that interval is tan. Let me say that again. For people who weren't in my class last year, this will be completely brand new probably, because very few people draw attention to it. That tangent, its length, is tan of theta. Okay? Now think about the way that works. For instance, think about what happens as theta, or in my case A, sorry my finger has bad aim. Think about what happens as that angle gets really close to 90 degrees. What's happening to tan? It's increasing, and it's increasing forever, right? At a certain point, namely, oh, sorry, my aim sucks. Namely that point, right there, when you try and feed in 90 degrees, what happens to the tangent? Well, it's a straight line that goes right across here and consequently never returns to the, there it is, never returns to the axis, right? So therefore, what is that length? It doesn't have a length, which is why if you think about what tan looks like at 90 degrees, I should say pi on 2, at pi on 2, tan doesn't have a value because the tangent never returns to the axis. Does that make sense? Okay, so, got to use the right hand, that's right. Okay, now I'm ready, now I've established what it's about. What does this mean for sine and tan for small x? There are plenty of ways to reason this, but I want to show it to you on here. I want you to look really closely at what's happening to these blue and orange lines. I'm even going to zoom in for you just so that it's really ultra obvious, okay? What happens as the angle x gets small? Okay, well watch. I'll do it slowly. Okay? As it comes down, look at what's happening. I'm going to zoom in even further. Oops, I went the wrong way. There we go. Sorry. Fix that. Square. There we go. We're going to go in even closer. Right? Look at what's happening to the blue and orange lines. I'm going to make the angle even tinier. Okay. Go away, email. Okay. Now, there are two things I want to observe. Number one, more emails. Anyway. Two things I want to observe. Number one, angles getting small. Yeah? Angles getting really, really, really tiny. Okay? What is happening to sine and tan? The lines are converging, right? They're converging together. In fact, at a certain point, like I zoomed in really far. If I come all the way back out, you practically can't tell the difference in sine and tan at this point, can you, right? Because that tangent is approaching a vertical line, which is what sine is. It's that vertical line, okay? So number one, they are converging. Number two, tell me what's happening to the size of sine and tan. They are getting small, and that should be no surprise. Like that's kind of an obvious thing because look, as you get closer and closer to 0, tan is also getting closer to 0. And so, for that matter, oh, that was badly drawn, sorry, there we go. So is sine, right? They're both getting small, okay? So my intuition, remember I told you, always try a guess, right? Always try a guess. My intuition is that sine and tan, and I'm gonna go one step further, the line y equals x, right? When they are small, they are practically doing the same thing, okay? Let me say that again, it's the plainest language I can. We're gonna make it technical in a second. Sine and tan and x. When x gets small, they are practically doing the same thing. That's what this intuition tells me. Now, using this weird diagram here, we're gonna prove it,